Oh, 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 oh. Dude. Dude. Dude! Ugh. Mm. Alright, let's read this paper. Two technical contributions are made. The first lies in a new representative model. Where is this shit? Hierarchical menus. Previous approaches used an assignment-based formulation. This is a novel combinatorial optimization purpose. So it's a combinatorial problem in nature, which is great, which means we won't solve it. To the design of the system describes a mixed integer programming. So you just program it and give it to a person, not me. Formulation to handle realistic size tasks. Okay. Frequency ordered groupings. So frequency ordered grouping is not something good. Well, okay, this is more about like designing menus in an app, not in an e-commerce. Here, like it says, frequency ordering grouping is not good because yeah, makes sense. You cannot, I don't know, fucking we have like, you know, on PDF we have all tools convert and e-sign, and we just if we grab the most frequent items from each one of them and put in one category, that doesn't make sense. Semantic matters, but in e-commerce, frequency implies popularity, good quality. Hence, the topmost items are not necessarily semantically indicative of what the menu contains. So, set covering problem, what does that mean? As follows. Given a finite set S and a list of some, not necessarily all, subsets of S, the intent is to find the minimal subcollection of disjoint sets such that all the elements of S are covered exactly one. What does that mean? Alright. So first of all, they should be disjoint groups, of course, and each element should be covered. Makes sense. Oh, okay, that's it. But I think one thing that doesn't match is again like we want that frequency ordered grouping in e-commerce be more present. Groups of group with clear intergroup boundaries. What is the group boundary? The second contribution is a new evaluation function based on information foraging theory. Previous literature focus. That's the good point about introduction. If you read one introduction, you get the idea about the whole literature. I want to also know if there is anything about this on e-commerce. So they have mathematics, which I like. So groups of groups. Also recommender system of recommender systems. Finally, it avoids placing unrelated commands, loners, in groups with poor association. Nice. Command in a group. There is one left. What does that mean? The convergence of these two ideas, the exact set covering formulation with the IFD based evaluation function, yields balanced and well structured menus, since the decision to include a command in a group and tab is modeled explicitly in the problem. Since it is, no post hoc steps are needed to segment the output. What does that mean? Alright, these are not interested. The rest of the paper is organized as follows. We present the succinct. What does succinct? Clear? Briefly and clearly expressed. Concise? Yeah, alright, sure. A review of the literature related to algorithmic menu design and related areas in operation research. So it is about operation research. It is about what we want to do after this. We define the design problem rigorously. Okay, that's great. And use the definition to inform a classical MIP, mixed integer group. That replicates the objective function using Fitts law and associativity as objectives. What is Fitts law? We then extend this formulation to utilize the IFT-based approach within the MIP formulation. Alright, okay. Problem definition. Let's go over here. And also, I like that these are things that people are writing paper on, and they are like experimental. They are not math heavy, by the way, because what like, okay, first you have mixed integer programming, but we cannot bring too much math here by nature, because it's like about how humans see this thing. What is a ribbon menu? Linear menu, I guess I know. Ribbon menu. So it's like a command bar. Why are they called ribbon menu? Ah, because like you said, home, insert, and then when you push home, all the... Right. So it's like they are... I get it. They are cross each other, like on the top of each other. That's amazing. Actually, I love that they are using this approach to study it. Yeah, they say, all right, we want to scientifically, as far as science lets us. I think a lot of it is just design, and it is about intuition. Maybe we cannot formalize it. It's like more of an art than mathematics, but they are trying. And better, the less an area is studied, we can say more things probably with less job, with less effort. So they want to minimize the overall time consumed by a user in selecting comments. Menu bar, command, groups, and then, oh, this is a group and menu tab. All right, let me show you. So this is what they are working on. Obviously, it is not e-commerce, but it is very related. What comments we should put in one group, how we should separate them. This is nice. However, our case is even more, because now even though they are grouped, they are in the same list. In our case, you want to say if they're grouped, you should add one more click and go inside. It's like file, edit, view, window, help case. I feel it should be very experimental, and I'm down. I signed up for an experimental research, so it's really good. But I thought, all right, we are gonna maximize like a utility, user's utility, or um, revenue of a platform, how to maximize that. Well, these are the things I didn't think about. I didn't know we can have them. All right. Anyways, so a menu item is a comment, or for our case, it can be, for example, an item. Demarcated. Demarcated. What does that mean?
Demarcate.
Demarcate. Set the boundaries or limits. Demarcate. Nice word. De-demarcate. The comma separate from other groups by a physical boundary in terms of a group. Yeah, that line. Multiple groups. By the way, it says physical. There is no physical thing. Multiple groups arranged in vertically aligned. Structure contains a menu tab or tab. Individual tabs have their specific identifiers. Yeah, for me it was like, oh, this stuff is just intuitive. Now they have mathematics behind it. There's again the variation of titles. All of these usually constitute the horizontally aligned structure as a menu bar for clear disambiguation. Can you read for me? I am tired. I don't want to read. Yeah, I am tired. What's wrong with this speechy part?
Foraging-based optimization of menu systems. Neeraj Ramesh Dayama, more does. The key terms utilized in our definition are illustrated in Figure 1. We call a menu item a command. A clearly demarcated set of commands, separated from other groups by a physical boundary, is termed a group. Multiple groups arranged in vertically aligned structures constitute a menu tab, or tab. Individual tabs have their specific identifier text or titles. All of these titles collectively constitute the horizontally aligned structure denoted as a menu bar. For clear disambiguation, we note that this paper addresses single-level hierarchy within menus. This means that one menu tab in the menu bar will involve one vertically aligned structure of commands that must all be visible or hidden as an indivisible set. This paper does not support any further internal rollover within the menu tab. While multiple groups are permitted within any menu tab, they must all be visible or hidden together.
I see. So
Given
this is
n
not our
commands,
case. This is exactly not our case. We want to have a layered structure. So let's just look at their mathematics and wait a second. They had introduction and now they have a huge related work section. So maybe let's continue this paragraph. They tell us.
the problem first requires these commands to be organized as ordered sets, each representing one group. Then, these groups are themselves.
Wait a second. Is it our case, by the way? So that section, file, edit, view, window, help, this is like categories. Within each category, we have categories, but all of them are shown in one list.
Organized into ordered sets that form individual tabs. Lastly, the tabs, in turn, are ordered in terms of the labels to be shown in the menu bar. This means that the overall layout is a problem of reorganizing the unordered set n into an ordered set of all n commands. The n commands are characterized by frequency of use f, associations a, and, optionally, location preferences l. We will denote the set of tabs as t, with individual tabs identified by index tel. All groups, irrespective of their tabs, are assumed to constitute an unordered set.
So frequency of use is good, they have it. Associations A, what is that? So each, maybe we want to have these terms. All right, we want to have the frequency of use. They were those JIs we had. Associations A. What is an association? And optionally location preferences. What is that? We don't have any preference. Well, we have maybe as ranking of tabs as T, set of tabs. What are tabs? File, window, help. With individual tabs identified by index ta. All groups. What are groups? Groups are within each tab. Unordered set of groups. All groups, irrespective of their tabs, are assumed to constitute an unordered set of groups C. Individual groups will be identified by indices C and C bar.
Of group C, individual groups will be identified by indices C, C. We note that any tab tau is itself an ordered set of some groups. Further, any group C set membership symbol C is also an ordered set of some commands. Finally, we use indices I, J to denote commands. Hence, the frequency of usage of command I is phi. The association between commands I and J is denoted as ij.
So we have one more element. So we have also fi. Each command has a frequency of use which is related to portion of the users. The association between commands I and J is denoted as aij. So this is one interesting thing that we want to have. aij, association between each two commands or items.
Problem requires computation of an ordered set T of ordered sets of groups of ordered commands, such that the objective function, defined via values of f, a, and optionally l, is optimized.
I think this is our problem too, because okay, we don't have the element association between alright, let me add it to my overleaf, and I can like address this paper as well. Let's go! Woohoo. can I cite this paper, by the way? It's just interesting for me. Oh, it is also human-computer interaction. Um, it's interesting for me that people are citing this kind of stuff. Like, what did I say? Citing? People are paying to research on this kind of stuff. For me, it's like, all right, try this menu. If it's good, then it works. But no, people wanna like optimize. It's interesting. Um, what's that? Where is it? Literature. Where is the reference? Who's optimized?
2.1 Objective function, costs to minimize. The problem definition discussed above did not explicitly provide the objective function. Traditionally, menu design has involved an objective function that is a weighted combination of two factors: 1. Time required to access individual commands, 2.
Sorry,
Mutual
objective and custom in a definition did not explicitly provide the objective function. Traditionally, menu design has a that is weighted combination of two factors: time required to access individual commands. So we're, instead of time, our equivalent is like eyeballing and layering, then mutual association of commands placed within. This is not present in our current setup. Current mutual
association of commands placed within any group.
Very interesting, by the way.
Example
This is
9,
super interesting.
17, 18, 19, 4, 20, 21.
21.
This objective function helps in two ways. First, the time required by any user, who knows the location of a required command, is exactly captured using Fitts law. So, the efficacy of an expert user, well conversant with the concerned application, is explicitly captured by the objective term. This ensures that the resulting menu system is indeed fast for usage by a well-experienced user. Secondly, the mutual association term helps a novice user in searching for any command quickly. Consider that a user is looking for the save as command. While exploring the menu, the user had encountered the save command in the first, leftmost, tab. The user remembers this location and also associates the required save as command with the known save command. So, the user is highly likely to search for the save as command in vicinity of the known save command.
I want to know
the
how they
second
model
objective
it
term,
mathematically.
representing the mutual association of commands,
With AI
ensures
generated.
that logically interrelated commands are collocated in close vicinity to each other. In this paper, we do provide a classical formulation using this traditional objective function in section 4. But then, we also propose a novel objective function based on the information foraging theory in section 5. For either formulation, our concept of cost encapsulates the efficiency of a broad set of users, while addressing the speed up for expert users who know the application well. We also wish to assist the exploratory efforts of novice users who are often searching for required commands with only a vague idea of requisite command names. 2.2 Scope. There exists a wide variety of interaction techniques for menus and menu-like paradigms for command selection 1. This paper specifically focuses on non-adaptive menus with hierarchical structures.
Oh, wait a second. There exists a wide variety of interaction techniques for menu command section. This paper is focused on non-adaptive menus with hierarchy.
The positions of commands are not assumed to change during interaction. We target designs wherein commands are organized by groups and tabs. The objective function does not consider all aspects of menu design, selection of labels or shortcuts, item length, etc. For the purposes of this paper, navigation occurs by selection of a tab and then a command within the tab. In this instance of hierarchical menu systems, only a limited subset of a menu tree can be visible at a time. While it is possible to extend the techniques in this paper to cover some other types of hierarchical menus, that discussion is beyond the scope of the paper. 3. Related work. Our work builds on results in 4 areas of related work: I. Modeling of search performance for menus. 2. Meta-heuristic techniques. 3. Integer program, IP, approaches based on the assignment problem, and 4. Facility layout and next release problems in operations research and software engineering. 3.1 Search performance and predictive models. Human factors in selection performance have been studied extensively. There is evidence of the following empirical effects. 1. Shorter menus are faster to use. 22, 6, 23, 2. Targets that are closer to the top are faster to select. 6, 17, 3. Linear menus with grouping, semantic or systematic menus, are much faster than random or alphabetical ones. 19, 7, 24, 8. 4. It is faster to select a target that is present in the menu compared to determining that the desired target is not present in the menu. 4, 5. Users get faster with practice, and this positive effect influences other, non-target items in the submenu. Also 17, and 6. Users often fixate
How
on one
many
of the first
research
3
has been
items.
done on
25.
this
Prior
thing that I was
mathematical
saying, like,
models.
oh,
4,
okay, just
26.
do one
Typically,
thing and if it works, it's crazy. I mean, maybe they are experimental research, of course. I don't want to have a theoretical work on this. Let's keep it in experiment. It's just first time me reading experimental papers, and they're so strange to me.
using nonlinear regression, capture some of these effects. Cognitive simulations such as EPIC 24, ACT-R 25, and computational rationality 20 capture more effects but are very computationally expensive. It has been found that users utilize various search strategies in menu navigation. 1. Directed search uses memory of element locations learned through practice for guessing where to search for. 2. Serial search progresses downward from the first or topmost command, after which items are sequentially examined one at a time. 6. 3. Random search selects an arbitrary position within the menu for fixation. 6, 24, and 4.
Dude, by the
Visually
way,
guided search is
I
based
just
on
want to remind
sampling.
myself, we don't have any rush. It feels these are not really what I like, but honestly I want to learn them. Yeah, let's learn them. Let's read 1 or 2 papers from them completely, and then we can go, okay, either say something new or just use what is already studied or invented, and then focus on our main thing. But we don't have any rush on, oh, finished. No, this is actually the research we want to do. This is unknown to me. I want to learn it.
Of visual landmarks such as the end of the menu or labels sharing visual features with the target. 4, 20. No previous mathematical model has precisely predicted the search behavior in a hierarchical menu. Sears and Schneederman 11 presented a model for split menus, where frequently used items are placed at the top of a linear menu, in their own group.
Well, first of all, there is so many similarities between this work and our work. I just want to know also if there is any, not Shapley, wait, where is that? Alright, I want to know, is there any information foraging theory work on e-commerce? Yes, there has extended uploading e-commerce index several academic and industry-related works by many foundational papers focus. Web navigation researchers have increasingly used IFT to study how to browse, filter, and select products on shopping platform. Product search and navigation application. Two 2001. Category and subcategory browsing. Is there paper? Yeah, we want to learn the system. Okay, they are all like Prioli and Fool. It seems we need to read them. Alright, we will read them, no problem.
Their model assumes that search time for frequently selected items is a logarithmic function of distance from the top, and for low-frequency items is a linear one. Lee and McGregor 27 proposed that selection time follows the number of pages needed to access retrieval of a given item, number of items per page, time needed to assess one item, keystroking time, and system response time. These models do not account for the effects of any other design factor than the number of items on a page or in a group. Bailey and colleagues introduced a free parameter to their model, indicating which of two search strategies is used. A gaze pattern was found wherein experienced users fixate on the first items in subgroups and then either drill down or not. However, the pattern was not captured well by the model, and the authors identified this as a target for further improvement. A recently presented Model 20 suggests that the optimal search strategy adapts to the semantic organization of a linear menu, allowing users to gaze more directly at relevant subgroups. This model relies on reinforcement learning, and it has been tested for predicting the effect of menu organization and menu length on task completion time and eye movements. With this paper, we investigate IFT suitability for a computationally efficient model capturing a key aspect of hierarchy-related decision-making, the decision to keep reading a submenu, tab or group, versus jump to the next candidate. 3.2 Menu optimization using meta-heuristic techniques. Most prior work 28-29 on menu optimization has used a meta-heuristic technique. Meta-heuristic techniques do not make explicit assumptions about the objective function, rather, they consider it as an oracle that tells them the objective value of a given candidate. As a result, they can work with any objective function, including nonlinear functions and even simulator models. In contrast to exact methods such as integer programming, meta-heuristic techniques cannot offer guarantees that the best design found is optimal. Moreover, meta-heuristic techniques, such as simulated annealing and genetic algorithms, include many hyperparameters. The tuning of these hyperparameters may affect their performance. Troiano et al. 30 used an index of accessibility and a user preference indicator to define objectives in a genetic algorithm, GA, solver that operates from the number of children of the item and depth of the menu hierarchy. Matsui and Yamada 31 explored objective functions to address selection time that consist of search and pointing, a penalty term for functional dissimilarity with other designs, and a menu granularity regularizer. As the authors noted, the approach is brittle, because results can change dramatically with small adjustments to objective weights. The state-of-the-art approach at the moment is Menu Optimizer 2. It uses a weighted sum from a selection time model, SDP26, and, as in Troiano et al.'s work, a structural metric. A weakness due to the use of the latter is that it produces results that are driven to be similar with previous designs. Further, the quality of the resulting solution changes with every execution. However, reasonable results can be produced quickly, within 5 to 15 minutes even on commodity hardware. The design of hierarchical menu systems has been restricted to the realm of meta-heuristic techniques, in areas such as simulated annealing 31, genetic algorithms 30, and ant colony optimization 2. Heuristic constructive approaches to optimization generate candidate designs using some heuristic that has been found to work in the domain. In menu optimization, this approach has been explored as a combination of exhaustive search and drill down 19, 18, 33. That is, it initially explores the most relevant solution directions, applying a breadth-first paradigm, then chooses a few suitable candidates for in-depth inspection. The methods presented thus far assume, however, that potential groupings of commands are stated a priori. This is a limitation, because the grouping predetermines the optimal solution. In this, the task becomes harder for the designer and relatively easier for the optimizer, which need only solve the ordering problem. Often, the grouping is a defining part of the problem at hand. The method described in this paper requires only associations among frequent elements, without any pre-grouping of elements. However, if the a priori grouping were to be already available, the methods in this paper can make efficient use of this knowledge. Association values can be expressed using a binary mapping, value 1 when concerned commands are in same group and 0 otherwise. 3.3 Exact methods, menu optimization as an assignment problem. Unlike meta-heuristic techniques, exact methods are guaranteed to find the optimal solution in finite time. However, the time required may be an exponential function of the problem size. Most interesting problems are NP-hard. The simplest exact method is explicit enumeration, wherein the objective value of each element in the solution space is evaluated and the current best solution, the so-called incumbent, is updated. In contrast, implicit enumeration makes use of relaxations that can be solved efficiently. One very popular form of implicit enumeration, which we use here, is branch and bound. This is one of the standard methods for solving integer, linear, programs. Keyboard layout design was defined in the 1970s as a quadratic assignment problem wherein the goal is to minimize the average time for
By
movement
the way,
between
if
letters.
I got to the point that, alright, this area is already studied enough, which sounds it is, then we don't need to solve it ourselves. We just use them and we will find what is the real problem. Alright, this part of the problem is solved by this paper. We don't need to do it again.
Assigned to buttons. Relaxations to the quadratic assignment problem, QAP, formulation have reduced solution times with integer programming, IP, solvers to a permissible range even with realistic data 34. The simplest application of this approach to menu design arrives at solutions for a linear assignment task 21. The formulation can be extended to full menu systems using hierarchical structures. Yet, designs created using assignment alone display systemic shortcomings. In particular, items are not assigned to groups, which precludes hierarchy. In addition, the most important items in each group are placed in the center, because of the associativity term. Moreover, though the design task has been formulated in integer programming terms, the problem has to be finally solved by means of meta-heuristic techniques due to the expensive nature of the evaluative functions required. 3.4 Selection problems in diet planning and service design. Menu planning, or diet planning, for the restaurant industry was defined as a linear programming problem in 1964-35 and has received sustained interest since 36.
So it was very
The task here is to select food combinations that meet dietary, gastronomic, and production objectives. The diet problem is a variant of menu planning for an individual or group 37. While food menu planning is not relevant for the design of menus in computing systems, the selection of functionality is. Functionality selected for an application or service must be accessed via a menu system. What is known in software engineering as the next release problem refers to selection of new software features 38 that accounts for user preferences, dependencies among functions, and costs. In a recent paper 39, Integer Linear Programming, ILP, was presented for the selection of functionality in interaction and service design. Here, we do not discuss the problem of how to select the menu commands, we assume the set n to be known. 3.5 Facility Layout Problem. Facility Layout Problem, FLP, is a class of combinatorial decision support system that deals with the location, placement, of facilities for factories 40. Facility location translates to the search for an optimal arrangement of non-overlapping indivisible entities within a given structure. The objective measure to be minimized is defined in terms of the weighted distance between the centroids of the entities being positioned. Within the broad FLP field, Closest
I
to
like
menu
that.
design
Wait
is
a
the
second.
multi-row facility layout problems.
The objective measure to be minimized is defined in terms of the weight distance between the centroids of entities being positioned.
Or 41, a variant that allows for a layout with multiple rows, in a predetermined number, to which the entities can be assigned. The entities all have the same size, with height equal to the common row height, distances between adjacent rows are equal, and entities can be assigned to any row in general. We note a parallel between FLPs and our problem. The arrangement of commands into unique rows within tabs matches the multi-row facility layout problem, MRFLP. The literature discusses mixed integer programming and also semi-definite optimization approaches for MRFLP, see Jen and Cheng 42. Regrettably, both approaches involve a highly nonlinear objective function, which adversely affects computational performance. We cannot expect these prior formulations to address problems with sizes beyond 15 to 20 menu commands and with additional complicating design considerations. Moreover, their objectives are different and not directly to menu use, which emphasizes comprehensibility and fast access. For reformulating the design task, a minimal representative formulation. The first part of our method is a flexible integer programming formulation for key decisions in designing a hierarchical menu structure. Intuitively, the problem is defined as ordered sets at multiple levels. We pursue a formulation that is compact enough to produce results with limited computational effort. It is flexible also in the sense that it can support evaluative functions of numerous types. We designate the formulation as a minimal representative formulation, MRF. The primary intention behind the MRF is to represent the structure of the hierarchical menu design problem, expanding from the assignment problem as dealt with by previous work. This lets us plug in various evaluative functions and thereby benchmark existing approaches to menu optimization. The formulation relies on principles utilized in the relevant technical literature but not previously explored for menu optimization. These principles have made it possible to overcome some limitations of the assignment-based approach in the hierarchical case. In particular, we can now express an evaluative function that refers to a user's navigation behavior both at the level of commands and at the level of sets of commands. We exploit this to construct an information foraging-based evaluative function that is more natural for hierarchical menu systems than the Fitts law and associativity matrix approach. See the next section. The MRF is developed here as a mixed integer linear program. We try out two evaluative functions to compare their. We exploit this to construct an information foraging-based evaluative function that is more natural for hierarchical menu system, to address the set cover related consideration of determining the intratab. The final outcome from the MRF is expected to represent the best possible results that can be obtained via techniques and approaches from prior literature. Technically, the MRF employs decision variables that map specific commands to individual locations, row numbers within tabs. To address the set cover related consideration of determining the intratab grouping of commands, we define decision variables to represent the number of groups and also the constitution of any individual group. Finally, to ensure the integrity of groups and row numbers, i.e., avoid holes between row numbers, we use a general precedence variable that avoids nonlinear terms while ensuring the expected computational performance. This results in a compact model with fewer variables and constraints.
Alright, let's see what it says. Decision variables XIC, C was set, command. 1 if command I is placed in group C, or C is for group. Command I is in group C, 1, otherwise 0. YIT if command I is in tab T, TA, 1 other. QC TA if group C is under tab TA. Okay. ZIJ, what is ZIJ? I don't remember. 1 if commands I and J are placed in the same group, so they are associated. ZIJ is 1 if they are in the same group, command I and J. WIJ is 1 in the same tab. Alright. R1 if the command I is placed on the rth row of the sum tab. If command I if command I is in the rth row of some tab, RIR row, and TI the time required to reach command I as indicated by Fitzgerald. SCC bar is 1 if the group immediately precedes group C bar on the same tab. S calligraphic SC means if group C is in the first topmost group on the sum tab. XC if group C is used has a non-zero number of commands. Okay. Beta R if tab beta TA if tab TA is used has a non-zero number of groups. Of course they should be used, no? If group C is data CC bar is playing anywhere before group C and so on. Starting position. So there are so many variables, and definitely they cannot have a closed form solution. Which is beautiful. I always think when you write a paper, you should have a closed form solution. No, actually, especially in experimental results.
Decision variables. The absolute positioning of commands is provided by R. Decision variables X, Y, Q define the unordered structure of the groups and tabs. Decision variables S and theta offer alternative ways to enforce the relative ordering of groups. The absolute positioning of commands is provided by
variables,
R.
They are
the variables W, Z, Psi, Beta ensure the sanctity of the overall mathematical model. By sanctity, we imply that these variables are intended to ensure that the decisions enforced by the other variables are in synchronization with each other. In the absence of W, Z, Psi, Beta, the results implied by the other variables can be infeasible or non-unique. The decision variable theta requires more explanation. Classical mixed integer programming formulations.
I forgot. Let's see.
Handle sequencing of elements by using an immediate precedence variable. This variable typically specifies that some element I immediately precedes some element j. The immediate precedence variable inherently dictates the relative ordering and also the collocation. There must not be any element k between I and j. In contrast, theta specifies the relative order alone and not the collocation. Hence, one or more elements may be present between I and j. This general precedence variable provides several logical distinctions from the immediate precedence approach, and it will be required for row numbering. The full set of constraints applied to these decision variables is covered in the appendix, subsection 9.2. 4.1 Example application, an evaluative function based on previous work. A key benefit of the MRF is that it can be used with a broad range of evaluative functions. Here, we replicate the two-fold objective function of Bailey etal2, which balances I, the time required to reach the commands, weighted by the frequency of use, against 2, the association of commands placed in a specific group or on a certain tab. Maximize ij, chij plus mwij, lambda f fidi. I set membership symbol n, j set membership symbol n, I set membership symbol n, 1. The parameters lambda f, lambda c, and lambda m are the relative weightages for access time, from Fitts law, intragroup associations, and intergroup, intratab, associations. We will discuss values for these weightages in subsection 5.3. We designate this as the two-fold objective because we are capturing two different metrics here. The term in A implies the effort in guessing the location of a command. The term in F captures the time required to reach a particular command when the user already knows its location. The results obtained for this objective function are presented in section 6, for comparison of the results to those obtained from the evaluative function based on the information foraging theory. 5. The information foraging approach. We develop a new evaluative function based on the information foraging theory,
Anyway,
IFT.
Take a look at the example.
4.1 Example application, an evaluative function based on previous work. A key benefit of the MRF is that it can be used with a broad range of evaluative functions. Here, we replicate the two-fold objective function of Bailey etal2, which balances I, the time required to reach the commands, weighted by the frequency of use, against 2, the association of commands placed in a specific group or on a certain tab. Maximize ij, chij plus mwij, lambda f fidi. The parameters lambda f, lambda c, and lambda m are the relative weightages for access time, from Fitts law, intragroup associations, and intergroup, intratab, associations. We will discuss values for these weightages in subsection 5.3. We designate this as the two-fold objective because we are capturing two different metrics here. The term in A implies the effort in guessing the location of a command. The term in F captures the time required to reach a particular command when the user already knows its location. The results obtained for this objective function are presented in section 6, for comparison of the results to those obtained from the evaluative function based on the information foraging theory. 5. The information foraging approach. We develop a new evaluative function based on the information foraging theory, IFT, 43. IFT models search behavior as utility maximization in a patch world. The theory is an application of the optimal foraging theory in biology, which describes the hunting and food search behavior of animals. An adaptive agent is assumed to change the patch as soon as the gain decreases to a level that it would make more sense to move elsewhere. Consider a wolf that has nearly exhausted the food in its current forest. Should it stay there, go to a nearby forest with rabbits, representing few calories per day, or travel a bit further to reach a different patch with deer, which are harder to catch but offer a greater gain. Application to menu interaction follows analogous reasoning. Just as in food foraging, the information ecology of a menu is patchy, that is, information about the target is unevenly distributed to patches such as groups and tabs. Because some of the patches are not fully visible and are accessed only via higher nodes in the tree, the agent must decide what to attend under uncertainty. From what is locally visible, example the first items in a group, the user must infer what the rest of the region may carry. Hence, the key to menu design is not how close an item is to the top, or to related items, but how economically the user can decide how well it represents the rest of the menu. To model this kind of information set 43, as is done in IFT applications in general, we assume that an agent's environment consists of patches indicative of a target to varying degrees and connected with distances, or time costs. Each patch is associated with a gain, a function describing how quickly information is extracted when the user is in that patch. In IFT, a nonlinear, logarithmic, function is used to model gain. It is continuous and has the property of diminishing returns. As more time is spent in a patch, less information becomes available, and a rational forager moves to another patch. The theory further posits that the user must make a decision for every set of commands attended. In the case of a menu, the user looks at the leading, top, commands in the set, example under file, and then makes a guess as to whether or not the set of commands may contain the desired command, example zoom in. If the user guesses that the current set should contain the required command, then the user will investigate further by reading, exploring, within this particular set. Otherwise, he or she discards the current set and moves on to the next without really analyzing the content of the current set. To make IFT amenable to mixed integer programming, we have formulated a sample discard, explore paradigm that allows avoiding nonlinearities, example logarithmic gain functions, but retains the essence of this foraging behavior. Intuitively, the sample, discard explore function captures 4 logical outcomes possible during search. 1 true positive, the user guesses that the set contains the target command, and it indeed contains that command. In this case, the cost during search within the set is the time consumed, by Fitts' law, to scan the list and move the pointer over the required command in the set. 2 true negative, the user guesses that the current set does not contain the required command, and the set indeed does not contain it. No further cost is incurred. 3 false positive, the user guesses that the set contains the required command, but it actually does not. The additional cost incurred for the set is the time consumed, under Fitts' law, to navigate all commands in the set. This cost is proportional to the size of the set. 4 false negative, the user guesses that the set does not contain the required command, but in reality it does. Now the user must, fruitlessly, analyze all succeeding sets, such as subsequent groups on the tab. We assume that the user begins the search by sequentially analyzing, sampling, the lead elements of every set encountered. On the basis of the decision made to discard or explore any specific set, the user invests the corresponding effort for that set. This process repeats until a true positive target is reached. 1 true positive. To make IFT amenable to mixed integer programming, we have formulated a sample discard, explore paradigm that allows avoiding nonlinearities, example logarithmic gain functions, but retains the essence of this foraging behavior. Intuitively, the sample, discard explore function capture. To make IFT amenable to mixed integer programming, we have formulated a sample discard, explore paradigm that allows avoiding nonlinearities, example logarithmic gain functions, but retains the essence of this foraging behavior. Intuitively, the sample, discard explore function captures 4 logical outcomes possible during search. 1 true positive, the user guesses that the set contains the target command, and it indeed contains that command. In this case, the cost during search within the set is the time consumed, by Fitt's law, to scan the list and move the pointer over the required command in the set. 2 true negative, the user guesses that the current set does not contain the required command, and the set indeed does not contain it. No further cost is incurred. 3 false positive, the user guesses that the set contains the required command, but it actually does not. The additional cost incurred for the set is the time consumed, under Fitt's law, to navigate all commands in the set. This cost is proportional to the size of the set. 4 false negative, the user guesses that the set does not contain the required command, but in reality it does. Now the user must, fruitlessly, analyze all succeeding sets, such as subsequent groups on the tab. We assume that the user begins the search by sequentially analyzing, sampling, the lead elements of every set encountered. On the basis of the decision made to discard or explore any specific set, the user invests the corresponding effort for that set. This process repeats until a true positive target is reached. This logic can be applied recursively at any level of a hierarchy where multiple options, sets, are available. In our application we assume 2 levels, tab and group.
Dude, this is a paper? This is just explaining previous works.
The insight is that the total time expended in locating a specific
the nature
command
of the papers I already worked on, like, when I read this kind of papers, like, what the fuck is happening?
is the summation of time spent in the 4 possible scenarios, weighted by the probability of the user making the corresponding decision for the relevant set. To obtain an estimate for the entire menu structure generated by an optimizer, the estimated times are further weighted by the frequency of use of individual commands. In addition to the search-related time components, motor selection efforts must be considered. Consider the case where the user already knows or remembers that some command I is in group C on tab tau at row number R. There is no search effort at all, yet the user still takes some time to traverse to row R on tab tau. As in previous work, this time is as computed from Fitt's law, and it depends on R and tau only. We address this time via the decision variable ti. We also need to quantify the user's expectation of a specific group or tab featuring command I. This expectation depends solely on the user's current knowledge of the presence/absence of other commands, such as J, in the group or on the tab. We quantify this expectation as follows. 1. If the desired command, I, is the leading, topmost, element of any group, the expectation is 100% for that group. 2. If leading element J of any group has a very high score, above 80%, for association with command I, then the expectation is 100% for that group. Conversely, a very low score, below 20%, for association between I and J leads to a negligible expectation. 3. For intermediate, unexceptional association score values, the expectation is scaled in proportion to the relative value of the association score with respect to the median one. Given a group C and an element I, we can judge the expectation of the presence of I in C by looking at lead element J of group C. Hence, the expectation of I's presence depends solely on the association between I and J.
Okay.
We denote this expectation as EE. We note that EE can be computed in advance through a pre-processing step, so it can be treated as a known parameter in the mixed integer programming formulation. We use EE to scale the efforts in every group for every command. 5.1 Mathematical Formulation. To develop an integer programming formulation based on IFT, we require decision variables that can uniquely specify the solution, the resulting layout, while enabling computation of the various efforts mentioned above. The specific decision variables, including computation of specific efforts,
Actually,
are
that's very
explained
good
below.
paper to read. You know why?
We note here that the decision variables
Because
described.
I was not reading, first of all, I know what is good in their literature. Like, maybe I wanted to solve that problem like in a closed form solution. It's stupid. Maybe here they just define a lot of variables and tell a lot of stories, and then they say we ran an experiment even without simulation, and that's good.
In the previous section are required
This is
to,
a paper.
along with their constraints. Equals 1 if command J is the topmost, lead,
Easy, writing
element
a
of
paper
group
should
C
be easy.
otherwise. 0 total time / cost for command I computed for group C. A equals true positive time / cost for command I computed for group C.
How do they measure
Sigma
this
equals
stuff?
false positive time / cost for command I computed
they have
for group
so many
C. A
variables.
equals false negative time / cost for command I computed for group C. Penalty incurred for command I if it is placed on non-standard tab T. The decision variable U assists in locating the lead
Do
element
they
in
have
any
any
group.
theorem? I don't think so.
Our IFT approach is based on this lead element, so its knowledge is critical. The variable encapsulates the expected total time, cost, or effort required to reach the command I if it were to be placed in group C. The value of will be a function involving the location of group C, its lead element and overall composition. This value of is expressed in terms of the three possible navigations, true positive, and false negative as covered by A, of,
However, I think
respectively. The objective is to minimize
their
weighted
results
cost.
can be used.
Weighting is by frequency of use, for the time taken to reach any command placed within any set. Such that minimize phi sigma upsilon sigma. In CEC TET. Plus alpha plus 20 plus 30. Ven, CEC, 2. This constraint is the key to the IFT approach and requires more explanation. Here, does not intend to capture the exact time spent by a specific user in finding a specific command during a specific single session of usage. Rather, it intends to encapsulate the weighted estimate of sum of searching effort and accessing effort for that command. The first term of this constraint represents the time, computed via Fitts law, needed to navigate to command I if its location is known in advance. But the wasted efforts from false positive or false negative, and even the searching effort from true positive, must also be counted while optimizing the location of C.
It's a big problem.
The remaining terms indicate the relevant costs incurred in searching for command I with respect to group C. Hence, is the summation of all concerned costs. The A values are weight factors to be specified by the designer. XU. 6 set membership symbol N, C, 3. In 4. These constraints ensure that exactly one command is marked as the lead element of every group. In addition, we augment equation 27 to ensure that command I marked as the lead element of any group C has its row number equal to PC. Next, we look at constraining the values of individual cost components. To calculate an individual cost component, we take the scalar product of the expectation value, probability of exploring the set, and the time expended in exploration of this set. For example, the expected expense of a false positive for command I in group C is as follows. X, V, 1 plus X, U, 6, JN, V,
and yeah, actually gives me a clear understanding of what a research
V is a suitably chosen sufficiently large
constant. Maybe you come
constant.
up with a simple mathematical
If the
and find a
V-related term
closed
is
form
neglected,
solution. There
then
is
the
no
false
point in
positive
it.
cost
Real
is computed in
problems
terms
are
of
here.
the size of the group that was needlessly explored. The V-related term voids the constraint if J is not the lead element or if I actually is present. Thus, the constraint addresses the case of a false positive occurring when group C is led by element J and the user is exploring C to search for I when I is not, in fact, present in C. Next, let us consider the case of a false negative for command I in group C, and greater than or equal to
You don't need a
1
deep theoretical
B,
result.
C,
Fuck that.
V,
I hate
2
it.
U X
Better.
6 J euro N VE 6. If the V-related term is neglected, then the false negative cost is computed in terms of the number of sets that will be needlessly explored. The V-related term voids the constraint if J is not the lead element or if element I is not really present. Thus, the constraint addresses the false negative case when group C is led by element J and the user discards C to search for I because of a low value for E. This means a high value for 1A. Next, we examine handling of the penalty related to the tab locations where certain commands are normally expected. T star greater than or equal to 1 to 1. Ven VE 7. Here, 7 asterisk refers to the preferred tab as specified by LE. If the command is not on its preferred tab, a penalty of 4 is incurred. 5.2 Handling of loaners. Loaner commands have poor association with other commands but may have a high frequency of usage. To avoid disturbing the cohesion of other, well-associated, groups, we strive to put all such loaners in a separate group of their own. However, the loaner group itself becomes contentious when the association for a specific command is not at either extreme, that is, loaner commands have poor association with other commands but may have a high frequency of usage. To avoid disturbing the cohesion of other, well-associated, groups, we strive to put all such loaners in a separate group of their own. However, the loaner group itself becomes contentious when the association for a specific command is not at either extreme, that is, when the command is not associated strongly with other commands but does not actually have an average association low enough to denote it as a loaner. Putting such commands in the loaner group makes this loaner group too large. However, the loaner group itself becomes contentious when the association for a specific command is not at either extreme, that is, when the command is not associated strongly with other commands but does not actually have an average association low enough to denote it as a loaner. Putting such commands in the loaner group makes this loaner group too large. We introduce a new hypothetical, invisible, command to the set N.
Look at this. This is beautiful because they have a lot of practical, pragmatic. What is the difference? Assumptions in the model. It's not just
will not be placed in the actual menu. It is only introduced temporarily to serve as a focal point for association of all loaner commands. The new command has the lowest non-zero usage frequency and no location preference, but it will still be constrained to be the lead element for its group, specifying U equals 1. The association of this command with all other commands is computed as follows. 1 For any command in, compute the sum of the association scores for I with all other commands j equals n, and designate the sum as sigma. 2 Find the largest value of sigma among all I equals n, and designate this maximum as v. 3 For any command I euro n, compute the value v, sigma I, to be designated as loaner. Factor wi. For the association of command I with is calculated as w, the square root of n. 5 If any command I has greater than average association with any one command in n, the association of command I with k is marked
what
as
this
0.
paper is saying is like, you can put any assumptions you want. You can add more variables and then solve it. From a mathematical point of view, it's not I love that this is just a pure engineering problem. Fuck mathematics, it is our bitch, it solves the problem for us.
After this, the optimization problem is solved for the augmented set n plus x. Naturally, the association score for strongly loaner elements with is quite high. This ensures that k serves as a loaner magnet, attracting all loaner elements to a single group. Further, the weight used to compute the association score from the
So it's
loaner
just
factor instead
explaining,
can
the
be
whole paper
modified
is
to control the
explaining why
size of the
these
loaner
variables
group.
are the way they are. It is very different from an econ theory paper.
No other constraints are required for the loaners. The loaner factor automatically handles the balance of populating the relevant group with commands while avoiding the problems of very large or very small groups. 5.3 Parameter values. The results from IFT, and even from the minimal representative formulation, are sensitive to the values set for A, as direct weights in the objective function. Any gross modifications to these values result in different menu layouts. For the results reported on in this paper, we have aimed for rough equivalence in settings among the objectives. No single term dominates in the overall objective function. To achieve this equivalence, we still need some rough information about the expected resultant layout of menus. So, we used the following as initial indicative intentions regarding layouts. 1. We prefer the menu layout such that the number of commands, rows, in every tab is not varying too much.
Theoretical paper.
As an example, we note that the baseline or commercial
theoretical.
menu structure in Notepad application has a very strong variation. While the Edit tab has 11 commands, the View tab has just 1 command. We would not prefer such a huge variation in our menus. 2. The maximum number of permitted tabs scales up as a logarithmic function of the number of commands to be placed. 3. We prefer not to use single element sets. If some command is so unrelated to all other commands, it is a suitable candidate for being in the loaner set. A single element group, as used in the View tab of the baseline version of Notepad application, will create several problems. Primarily, it hampers the access time of all subsequent commands. Secondly, it also increases the total cost of all false negatives for previous commands. The intentions listed above are not enforced as hard constraints and are not included in the objective functions. Rather, they are used as indicative guidelines while designing the values of parameters A. Consider the values of A and X as presented above in equation 1 for the minimal representative formulation. For a data instance involving n elements, we first expect that roughly log n tabs are allowed and every tab has log n commands on average. Assuming that the overall user interface is of width w and height h, the term mean fitting in equation will have a value of the order of magnitude of roughly 2 log n. The term
based on what?
Cngn ijzij will be in the general vicinity of n superscript 2/2 for a sufficiently large canvas. WNH. And for lower value of n, value of WNH2
based
log
on any proof?
n is substantially larger than n2/2. To ensure that the two terms have comparable impact in the overall objective function, the value of lambda c 2WHN log n times that of lambda f. A similar approach is used to initially set the should be around lambda values for IFT. However, we expect that the designer will fine-tune the results further. It is expected that the final relative values will be ascertained through trial and error over a large number of results.
Yeah, what the fuck?
6 results. In this section, we assess the quality of the optimized designs and report on performance quantitatively. 6.1 Task instances. The approach was tested with 3 realistic design scenarios, selected for their representativeness, size, and diversity as cases. Our goal was to use a wide range of often used applications, where the names and meanings of most commands are clear to typical users. Users who are already conversant with the commands will also have some ideas and expectations as to mutual associations, preferred placements, etc. With these objectives, we chose the following applications as test cases. 1. The classic Windows Notepad trademark application is a widely used compact, elementary text editor. The existing design involves 23 commands, distributed across 5 tabs. 2. The Adobe Acrobat Reader trademark application is a commonly used reader for files in PDF format. Version 11 of this application has a menu system with 46 commands, distributed over 5 tabs. 3. Mozilla Firefox Trademark 3.6 is a well-known browser application. Its menu system has 51 commands, spread across 7 tabs. These instances are represented by means of the following parameters: names, text strings, and relative frequency values F for all commands, 2. Association score A for every pair of commands, and 3. Optional, location preference L for any of the commands. To ensure the practicality of the instances, the authors implemented a short exercise in which 2 external designers, students enrolled in an human-computer interaction program, were asked to rate 2 parameters independently: how many times in the course of a typical usage session is a specific command required, and 2. How closely are the 2 given commands related to each other.
God.
The answers were quantified to yield the frequency and the association score, respectively. We found the disagreement to be below 1%, so the values from the 2 raters were accepted as the data instance specification.
This feels like
In the
a
discussion
bio
below,
paper.
the incumbent menu is the menu that exists in the commercial applications as of the time of writing. This is referred to as the baseline design.
Jesus.
The baseline designs for all data instances are provided in Appendix 9.3. The layouts produced via the optimization method proposed in the paper are denoted as the optimized design.
So why is this good?
Optimized
Why
designs
they
are
compared
covered in
to
Section
other
6. 6.2 Implementation and Numerical
This
Performance.
is really research, by the
The
way.
mixed
To be honest,
integer
I
programming,
think this is research.
MIP.
Research is not solving a math problem only. Research is like, I'm curious about this. I want to see how it works.
Formulations were coded in the Java
Maybe 100
trademark
years
SE,
from now we have a
build
foundation.
1.8, PLAR form. These formulations were solved using IBM trademark Plex trademark 12.6.2 solver.
Insightful is
On an
that
8-core 64-bit Intel trademark
You can
i7
understand how
trademark
it works.
processor running at
People
2.8 GHz with 16 GB of RAM.
What is this?
The MIP solver was used with Concert
Oh, the
trademark
solver.
technology in conjunction with several
Interesting.
customized
I like this
callbacks.
part too, because they didn't.
Computation times for the 3 cases are given in the mixed integer programming, MIP, formulations were coded in the Java
Perfect. We can
trademark
talk
SE,
about them like
build
this too.
1.8, PLAR form.
That's why I like to read
These
this
formulations
paper. We cannot solve the MIP like, alright, this is a closed form solution. But we can say, alright, we solved it with this thing. We didn't even optimize for the
were
solver.
solved using IBM trademark Plex trademark 12.6.2 solver.
I can say this stuff. I
On
love
an
it.
8-core
I love it.
64-bit Intel trademark i7 trademark processor running at 2.8 GHz with 16
It's doing
GB
a
of RAM.
project. That's a
The
project.
MIP solver was used with Concert
That's solving a
trademark
math
technology
problem.
in conjunction with several customized callbacks. Computation times for the 3 cases are given in Table 1. These times are reported as averages over multiple computational executions,
this paper,
with
by
different
the way?
values for weight functions lambda and
Easy
phi, for
optimization.
values as computed in subsection 5.3. We note that for extreme values of lambda and phi, much shorter computation times were observed. For example, if lambda f lambda c and lambda f lambda m are set, then the minimal representative formulation objective does not really consider the association between commands at all. For such an extreme setting, the corresponding problem can be solved within a small fraction of the computational time
They're
listed.
talking about some of the challenges they
The
have.
computational performance strongly depends on the chosen parameters. The listed performance is for the default versions of the MIP formulations, where the raw model is passed to the solver without making any attempts to improve performance. In practice, there exist several MIP techniques to improve computational performance. Further, the performance improves substantially when we start with a known, existing
It's just
solution instead of
descriptive
starting
things.
from
There's
scratch.
no theorem.
In
It's
our
very
case,
descriptive what
one
they do.
feasible solution,
I
The
did this,
existing
that
layout
was fun.
is always known,
Then I was
so this
tired, I
technique can
went
be
back
easily
home.
utilized.
Tomorrow I showed
However,
up, I
the
solved
discussion
another
of such
problem.
MIP techniques
This
is
time
beyond
I
the scope of
changed
the
this
current
parameter
paper.
and I
Our
saw,
focus is
wow,
to
this is
demonstrate the
crazy.
efficacy of the menu design approach and not the numerical
Then I
method.
made this table in
Table
Microsoft
1.
Word.
Computation times for optimal. Although the computational effort excludes the use of these solvers in
What are the
interactive design
insights
tools,
this paper
they
is
appear
giving us?
satisfactory with regard to the problem considered here, especially for one-shot optimization. Developers of
I mean,
professional
everybody,
software
okay,
should be
for
ready
me, the problem is that it is clear. I mean, I love that this can be a paper. I want to write paper like that too. But what is the point of this paper? Like, writing the optimization problem, what was the novelty? What was the genius? Like, alright, you can write integer programming or mixed integer programming. Yes, somebody adds some parameters, somebody else added some other but like there is nothing that was like, oh, if you didn't do that, nobody knew it. Everybody knew it. It was just so obvious, nobody write it down. And then you gave it to an optimizer. I mean, I love that. If it is the case, I can publish thousands of these
a few
papers.
hours or even 2 weeks of computational effort to ensure the quality of their menu design. This can be further speeded up by using dedicated hardware. Our computations were done using a commodity laptop. Secondly, the data shows that using
What was
IFT does not
challenging? Okay,
significantly
what was
impair
challenging in this paper? What was something we didn't know and we find out?
performance relative to that with the earlier two-fold objective approach. 6.3 The two-fold objective approach. We now present designs generated via the algorithms discussed earlier for the data instances specified in subsection 6.1. The results for the 3 data instances with the two-fold objective approach are provided
Maybe some people get
in
insight.
figures 2, 3, and 4.
Maybe it's valuable for
Figure
other
2,
people.
a menu optimized for the Windows Notepad trademark text
I'm
editor
just
with the
stupid.
two-fold objective minimal representative formulation approach. Figure 3, a menu optimized for the Mozilla Firefox trademark browser with the two-fold objective minimal representative formulation approach.
Great.
Figure
Actually,
4,
I love this
a menu
paper.
optimized
Maybe
for the
I
Adobe
don't
Acrobat.
understand it. The other
It
people
should be noted that the optimized menu for Notepad has fewer tabs than the
I just wanna
baseline,
publish
commercial,
and
design.
help other people and
This
get
is
my
because the
PhD.
Notepad data instance involved high scores
is
for
better than
association
this?
between commands. The association values for pairs of commands for Acrobat and Firefox were comparatively low. The sparse association led to a wider layout with
Alright,
more
guys,
tabs
I'm
and
gonna
smaller
stop.
groups. The argument extends to the